All right, hello everyone. Welcome to our video class this is our first video for class 9. Hope you had a good spring break. So whatever day you're watching this, if it's Pi Day, March 14th, you guys are March 15th, St. Patrick's Day. The field of 68 may have been announced for the men's and also the women's basketball tournaments. Division 1, I don't think RMU is going to make it this year. I don't think they had quite as good of a year. So by the time we record this, all that will be decided. So we'll see how this goes. It's kind of a weird energy just sitting in a room talking to myself, basically. But hopefully you find this class to be very productive and very enjoyable. So we're going to organize the class into, I think Andy had the idea of, he said, in different topics. So I'm doing 4 videos, so I don't want any one video to be super, super long. We're going to spend most of our time on credibility. We'll talk about the full credibility standard and also the complement of credibility. So this is video 1, which is the full credibility standard. Video 3, we're going to cover a couple topics from chapter 11, namely increased limit factors and deductibles primarily. And then video 4 is kind of miscellaneous stuff where we're going to talk about the project, I want to go over lifetime value question, and then we'll also do some preparation for the exam. So this is video 1, which is the full credibility standard. Okay, so we touched on this briefly last week, or on March 1st. It's last week to me. I'm recording this on Wednesday, March 9th. So forgive me if I say last week, because it was only 8 days ago for me. So credibility really is it's a measure of your experience, a measure of how much stuff you have, how much you can believe your data. So it's easy to say the more stuff we have, the more exposure units we have, the more data we have in which to base our analysis, the more that our historical experience will equal the true experience. We talked about it before, in which, the credibility of, if we have just one driver, obviously that's a lot of luck goes in if we wanted to base our rates based on that, the one and only one driver. So the more experience we have, the more drivers we have. 2 drivers, 10 drivers, 100 drivers, 1,000 drivers, 10,000, 100,000 drivers, or 100,000 vehicles. The more we go, the more we can really believe that we have enough data to make a decision. This is really you can really call this the signal and the noise. One of my favorite authors is Nate Silver. I've listened to a lot of his podcasts. I follow 538 fairly closely. They do a lot of really good stuff with sports, with politics. If you've ever haven't seen it, it's called 538, written out, the words FIVE 38 all written out, .com. He wrote one of the best books I've ever read. I encourage you to read it. It's called The Signal and the Noise. And really, he talks about predictions, and he really talks about how much noise is involved with predictions. So when there's one driver, say we're basing our rates only on one driver, there's going to be a whole lot of noise. A whole lot's based on luck, and you really can't believe that the one experience. So this is really, how much signal do you have? Think about credibility being how much signal you have and how much noise, or how stable will your analysis be? So how much of this luxury do we have? We don't always have enough data in order to make our decision. So if we're doing experience, say, for a class of business or a whole state, or if we're looking at 16 to 19-year-old drivers, if we're looking at 16 to 19-year-old drivers in a state, we may not have enough data in that state to say, hey, I'm confident that this is mostly signal and very less noise. I know we talked before about workers' compensation insurance. If you're doing experience for, excuse me, if you're doing loss experience for high-rise construction 4 to 6 stories off the ground, for example. You probably don't have a whole lot of data to base your experience on. So you're going to have a less signal, and more of that experience will be noise. So then, what do we do? What do we do when we don't have we have mostly don't have a lot of signal. We have mostly noise. What do we don't have a whole lot of data? So the first thing we can do to make it all consistent is we want to quantify how much we can believe in our data. So how can we say by using numeric um, using numbers how much we can say I can believe this data this much. So we know that. But then the other thing we need to do then is what else do we supplement the data with? Okay, that's great. We know we can believe our data, say 30%, or we can believe our data at a 30% level. So then where does that 70% go? You have to select something to supplement the data with. So this video, we'll talk about the first piece and the quantification of how much we can actually believe our own data. Okay, so the term that we use in order to the amount that we can believe our data is called credibility. Credibility sometimes feels like believability, or you don't have a whole lot of credibility, or I have street credibility or something. But credibility is also an actuarial term, and this is directly from ASOP 25. What's the predictive value that we can attach to a body of data? So that is the actuarial term from 1996. It really hasn't changed. It's part of the actuarial standards of practice. And the letter Z is used for that statistic. So whenever you see the Z, or our Canadian friends say Z, that is the level to which we can believe our data. So this is where the Z will be the value attached to our own data, and then that will be the value that we blend our estimate with the related estimates. Okay, this is very important. This is huge right here. This is a good exam question. What are the 3 criteria in order to measure credibility? So what does Z have to be? So think about going from 0 to 1. 0 means you have no credibility. I know sometimes I've been told I have no credibility. No, just kidding. So sometimes we'll believe we have 0 means you have no credibility. I can't believe that data at all. And 1 means fully credible. So that's the 0. Z is a number from 0 to 1. It could be a percentage, or it could just be a decimal. There's 3 criteria needed to measure credibility. Z can never be less than 0. So there's no such thing as negative credibility. Z must be less than or equal to 1. So it has to be capped at fully credible. So that's obvious. 0 to 1. The Z is between 0 and 1. So we're saying number 1, Z is between 0 and 1. Secondly, Z should increase as the size of the risk underlying the estimate increases. So it has to have a positive first derivative. The more data you have, the more information you have, Z can never go down, if you think about it. So if I have 10 drivers, can never be more credible than, or 10 vehicles can never be more credible than 100 vehicles. So Z should always be increasing as the size of your estimate increases. Secondly, this is important too, as the size of the risk increase, Z should increase at a decreasing rate. So you can call it a negative. A negative second derivative. I think it's called concave down. So going from 0 to 10 should get more. Z should go higher than going from 10 to 20, 20 to 30. Or think about going from 0 observations to 100 observations. Should be a greater change in credibility than going from 1,000 observations to 2,000 observations. This is a little bit nebulous right now, so we're going to look at this. I'm sorry. There's also 2 methods to determine credibility. This is called classical credibility, which we'll spend more time on, and what's called Bielmann credibility. So we'll go. We'll talk about all 3. or all two. I'm sorry. There is a third which we're not going to cover. It's called Bayesian credibility. We won't cover that at all. That's kind of a really complicated one. Okay, so have we? So this is an example of credibility. So this is just credibility. It's a straight line going from one claim. Let me go to a pointer here. Going from one claim to 1,082 claims. You'll see 1,082 is kind of a magic number as we move forward. So here we go. Credibility, it just increases. It just goes up at a flat line, essentially. Strictly. So have we? Is it bounded between 0 and 1? See, when we reach 1,082, we're considered to have a credibility of 1. We have one claim. We have a credibility of near 0. Is it bounded between 0 and 1? Yes. Is it a positive first derivative? Well, yes, it is increasing. Does it have a negative second derivative? No, it is not. It is not concave down. You can see the second derivative is 0. This looks like just maybe a y equals, y equals some factor of x. It is strictly linear. So you cannot have credibility increase like this. Remember, I said going from 1 to whatever this point is here is the exact. Every time you increase an observation, you increase credibility by the exact same amount. That is not a negative second derivative. So this is not a necessary criteria for full credibility. Let's look at the second one. Is it bounded between 0 and 1? Yes, it is. Again, you can see this is kind of a more of a logarithmic type curve. Does it have a positive first derivative? Yes, it does. It is not. It's going up all the time. It never goes down. For more claims. Does it have a negative second derivative? In this case, it does have a negative second derivative. Because you can see the change in credibility. Going from 0 to 0.2 is a small amount of claims. Going from 0.2 to 0.4 is a larger amount of claims. Going from 4 to 6 is an even larger amount of claims. So credibility increasing logarithmically is typically what you want to see. That's typically it fulfills the necessary criteria for full credibility. Let's go to slide 3, or let's go to example 3. I'm sorry. So this is kind of a little bit of a weirder looking curve. It appears to be logarithmic. It rises very quickly at the beginning. It never actually hits 1. You'll see this. You'll see this kind of distribution. This is more of a Bielmann credibility distribution. So credibility is bounded between 0 and 1. Yes. Now that's pretty obvious. Positive first derivative. Yes, it's always increasing as the number of exposures increases. Is it a negative second derivative? Let's see. Eyeballing it, it does appear to be concave down. So the difference between one, I like using 0.2. The difference from going from 1 to 0.2 is. I'm just going to use the pen here. See if this works. Going from 1 to 0.2 is like this. Going from 0.2 to 0.4 to 0.6, you can see the sizes the sizes between here gets a little bigger, even bigger, and even bigger. It actually does indeed have a negative second derivative. So this one does, again, follow the example for full credibility. You'll see this is actually called in the Bielmann credibility world. Okay, so what is classical credibility, or what is what we call limited fluctuation credibility? I'm going to put this view back on here. Yes. Okay, so what's called limited fluctuation credibility? I'm trying to get my pointer back here. I apologize. Okay, we're recording again. Nice. You can pause the recording too. That's nice. So Okay, limited fluctuation credibility. This is the one that's most frequently used in rate making. So again, the goal of credibility is to limit the effect of any sort of random fluctuation or any sort of noise. You want to measure your signal, and the signal that you want to obviously use your own data as much as you possibly can, but you want to maximize the amount of noise. So the estimate for credibility, this is the big formula, is what's called Z, credibility, times observed experience. That's the experience that you're actually seeing, your drivers or your homes, your real experience, plus the complement of 1 minus Z, so it's a weighted average, times the related experience. We'll be calling that a complement of credibility. That's going to be the topic of our next video. Okay, so I'm not going to derive this on a OneNote board. I'm actually going to derive this on the next slide. But we have, so it's very important that we know what our algebraic, what our symbols are. So Y is represents the total number of claims. So that's the, and so we're going to use claims. We can also use exposures as a proxy for claims. We'll get into that. But typically you want to measure the total number of claims or the total number of expected claims because you're typically looking at loss experience for credibility. S is the total number of loss. So S is the total amount of losses, or the total dollar amount of your losses. So you want to determine the expected number of claims that's required for observed experience to be fully credible. So E of Y, the expected number of claims. Now we use total number and expected number interchangeably, and that's going to be okay. So expected number of claims can also be the total number of observed claims, but using exposures you can say expected claims. So that's why we're going to use some terms we use interchangeably. So the real key here is you are considered fully credible when the probability P. So you're using really what's called a confidence interval, if you will. So the probability P is high enough that the observed experience will not differ from the expected experience by an arbitrary amount K. And again, these are all arbitrary numbers. That's one of the one of the downsides of limited fluctuation or classical credibility. But this is easier to say rather than using P's and K's. Let's look at an example here now. An example. So our claim sample is fully credible. So the losses we have, the total number of whatever that we're measuring, is fully credible when we're 95% certain that the observed experience will not be different from the expected experience by 10%. So kind of plus or minus 10%, if you will. So it's essentially, if you want to think about it, I like to think about it as a confidence interval. 95% certain the observed experience will not differ from expected by 10%. So this is all kind of weird and nebulous. We'll look at the derivation here in a second. But the other thing that we really want to talk about, though, is what we call the central limit theorem. This is the big shortcut. This is how we can add this. The central limit theorem allows us to measure credibility. So the central limit theorem says if you have a population with a mean and a standard deviation, so mean of mu, standard deviation of sigma, and you take a large enough random sample from the population, the distribution of the sample is approximately normally distributed. So we can actually use those fun normal, the standard normal curve to allow us to know the expected number of claims. This is a pretty big jump here. This is a pretty big assumption, but in general, it's usually pretty good. Sometimes it doesn't seem like it's good. It seems like we're taking some shortcuts, but typically this isn't too bad. So let's now go to our derivation. I'm using PowerPoint to do this derivation as opposed to using uh, the board, just to make it easier on you and easier for the video, less flipping around, and that'll be easier to save too. Okay, so the number of claims for full credibility. It's good to kind of derive this using algebra. Okay, so this is our the probability that our expected sample S, or the expected losses, we want the probability P that the expected loss differs from 1 minus K. So say if K was 0.5 or 0.055% to be probability of 95 for probability of 0.95 to 1.05 of the expected value. So this is our confidence interval. The probability that we're within our confidence interval is probability P. So the first thing we do is that exciting and fun central limit theorem. We want to apply that theorem to use the standard normal distribution. So hopefully all of you are good at math, and all of you have taken this. All of you know exactly what the standard normal is. So the standard normal curve is S, your actual value, minus your expected value, divided by the variance of that value. And then of course you take your probability, you divide everything by the square root of the variance, and you get that formula here. You get the 1 minus K ES minus S divided by S minus ES, then the quantity 1 plus K times ES over S. So that's just taking this, dividing it by the square root of the variance, or the standard deviation, if you will, and then the with our formula at the top. Next, so since the normal distribution is symmetric around its mean, and again, that's the beauty of the central limit theorem. The mean is equivalent to 1 plus K E of S minus E of S divided by the square root of variance, or that little standard normal Z of P plus 1 divided by 2. So you would actually use a standard normal table. Okay, one more simplifying assumption here. So we're doing this again. You see a lot of simplifying assumptions here, which is kind of a blessing and a curse. By using you're making some assumptions, which makes it easier to compute, but the assumptions sometimes take the teeth out of it. So the simplifying assumptions are the exposures are homogeneous. So each exposure has the same expected number of claims. Not always the case, but from an independent standpoint, that's what we use. Claim occurrence. This actually happens a lot in P&C actuarial. This is actually fairly true, that usually the occurrence of a claim follows a Poisson distribution. This is not that crazy of a reach as it might be, because claim frequency actually is pretty Poisson. So, and the beauty of the Poisson distribution is the mean is equal to the variance. And the second thing is there is no variation of the size of loss. We are assuming constant severity when we do this. It's not always perfect. So you want to make sure when you have a sample that it's independent, and also the constant severity is going to be it's just going to be good enough to be constant. Again, this is very it's very a lot of leaps here, but this is what we do for full credibility. And these, again, it does come out to usually be it comes out to be not too bad. Okay, and then so you have your final formula is simply K times your expected value of your number of claims, your expected value number of claims divided by the square root of the expected value number of claims. That is your P plus 1 over 2. This is how we'll go here in a second to determine how we calculate this. There you go. And then it's E of y. So your E of y is equal to this. Here you go. The number of the standard normal, your standard normal z divided by your probability squared. So we will do this in practice in just a second here. Keep wanting to say any questions, but there's actually I'm not talking to anybody. Okay, so let us go to our next slide, and you can you'll see this a lot as we talk about classical credibility. You'll see your numbers here for the standard normal curve. The 90%, your z-score is 1.645 for a p of 90. For a p of 95, your z-score is 1.96. And for a p of 99, your z-score is 2.575. Those are typically the numbers that we use. We can use other numbers if we want. You will not be expected to memorize them, but these are like typically the numbers that we like to consider. So let's go to Excel first and talk about full credibility standards. So hopefully this transition works. Let me see here. Yes, here we go. So we're gonna work our way through a couple of examples here. Okay, the other beauty of doing this, doing a recording is you can pause and get rid of a couple of things. So, okay, so we're going to look at several examples here for full credibility. We're going to go over some of these fairly quickly. Then I will leave some of these to I'll leave some of these to you to calculate, and then I will pause the video, and then I will go over I'll go over the actual answers. Pause the video to give you a chance to actually to work on them too. Okay, so let's talk about. We're going to go through the first couple here. So, okay, so you want to know a probability of 90% that you're plus or minus 5% of your actual estimate. So the first thing you do is you look at your z-score. So the z-score is in the normal distribution table, which I conveniently put over here. So your z-score is going to be 1.645. So the number of claims, now that you have these two things, the number of claims you'll need for full credibility is going to be basically 3 divided by 1. Remember, 3 divided by 1, and then you square the total. So 1.645 divided by 0.05, and then squared. There's the 1082. So remember I said before how 1082 is going to be used very frequently, and there you have it. So the number of 1082 is the number of claims for full credibility that you're 90% certain that you're plus or minus 5%. Okay, we'll do exposure. We'll do exposures in a second, but let's look at claims first. For now, you're going to be a little bit. You don't care if you're at least within plus minus 5. Let's say I want to be a little bit less certain and plus minus 10%. So your z-score again, 1.645. And now the number of claims for full credibility is going to be 1.645 divided by 0.1. And let's square it again. Squared. Now only 271. So I'm okay with this. You're saying I'm okay with being a little bit more off. I'm okay with being 90% and plus minus 10%. So I don't need to be that super. I don't need to be that super confident. So now you need 271 claims for full credibility. If it sounds arbitrary, it's because it is. That is this is one of the pluses and the minuses for full credibility. This is really where it comes down to really knowing your data and knowing how confident you think that you can be. So and maybe how much how much you think severity is going to the expected severity is going to be constant, or how homogeneous you believe your data is. Maybe if your severities are going to be low, for example, you're doing maybe something like auto collision or auto comp. Maybe a lower number of claims is better than if you're doing something like auto BI, where severity is very high. Maybe you're going to want to have more claims for full credibility. So let's slide down to this next one here, the third one. So now we want to be 95% certain. Now we're not 90% certain. Now we want to increase our certainty. We want to be 95% certain that we're plus or minus 5%. So our z-score again is for 95% is going to be 1.96. So once you know these two numbers, you can calculate your credibility, your full credibility standards by a number of expected claims or number of claims. So 1.96 divided by 0.5, and you square it. How many claims do we need now? Now we need 1,537 claims. So by increasing your probability, you want to be a little bit more exact. You increase the amount of data that you'll need to be fully credible. We'll do one more here, then we'll get to exposures. If you're wondering why we're ignoring column 6. So again, so we will have 1.96. I like my place values are all lined up. I'm going to do this too. Big fan of lining up place values. So now again we're lowering our standards a little bit. So we're lowering this means we're lowering our standards. We're lowering our full credibility standards. Number of claims needed for full credibility is 1.96 divided by 0.1 squared, 384 claims. So you can see how we continue to, you can see also like K is really a big driver. P isn't as large of a driver for full credibility. K is certainly a very, very large driver. So if we say we only want to be plus minus 0.1, 0.01, you look at 1%. So K going from 10 to 1. Now your number of claims for full credibility is 38,000 claims needed for full credibility. Normally you don't need that many. That's really what we're doing here. Okay, let's jump over to exposures for a second. So sometimes you don't have claims. You would rather use exposures because this is really, we say number of claims. It's really truly the number of expected claims is if you look at actuarial literature. And I said before, we're going to take claims and take expected claims and kind of go, we're going to go back and forth a little bit. So this number, all you have to do is in order to go from claims to exposures, you take your projected frequency, you just divide by your projected frequency. So if our projected frequency is 5%, just take number of claims divided by number of exposures. I'm sorry, number of claims divided by frequency, my bad. And you have 21,648 expected claims. And again, if you just go down, we all have this has the same projected frequency. Say this is something like homeowners, which has a frequency of about 5%. The number of exposures, the number of homes you needed to be fully credible varies greatly. So if you're doing homeowners insurance, this is where expected severity comes in. So if you're doing homeowners insurance, for example, and you're doing all homes of 100,000 to 200,000, say you're doing all basically the same size of homes, you may not need as large of a standard. So maybe you would use the 5,000 claims for full credibility because they're all relatively small homes, maybe all the same general area. There's a lot of homogeneity. Say though you're doing something like you're looking at a sample of $1 million homes, or it varies greatly from small homes to large homes and homes all throughout the United States. There's not a lot of commonalities in expected severity, for example. then maybe you want to be a little bit more exacting for being close, and you would use a full credibility standard, say, of 21,000 exposures. And there's nothing magical. 21,648. You could easily just say 22,000. Sometimes better to have those simplifying assumptions. Okay, so you can so feel free to pause. Feel free to pause this right now if you want to do. If you kind of want to look at 9 through 12, this would be the part I would do in class. It is perfectly up to you, but I am going to also do the last 4, and I'm going to go through them a little bit more quickly. So we're going to look first at 99%. If we have a 99% probability, a very high probability, that's your z-score of 2.575. I'm going to do these two together here. And then we have 5% and 5% and 10%. I like seeing what is the impact for each one of these here. So 2.575 divided by 0.5, square it, and we get 2,652. And 99% and 10% is number of claims 663. There's a lot of ways you can measure full credibility, and so I like to go to help you with the actual thought process of full credibility. I really like to give you that perspective, kind of what this is where some of this really becomes in. Also, one thing I like about PNC actuarial work is it is kind of an art and also a science. I like the fact that there's both. This is really, it really helps you not just, there's no fully truly right answer. There's never any true fully wrong answer. So you have to think. And I like jobs where you're not just applying a bunch of formulas, but you're also using your head. So what are these last two? These last two they're essentially the same. So 5%, 95% was what? 1537. 5%, 9%, or I'm sorry, 10 and 99% was this one here, 663. But now if we change our number of claims, I'm just filling down the formulas, is, 100, you need 100,000 exposures for 5%. If, say, you're doing something like auto liability, might be property damage, might be 1.5. A projected frequency a little bit lower. Maybe not property damage, maybe more closer to liability. Liability usually less than 1, but 100, 2,000, and 44,000 exposures. So this is how you calculate. This is how you calculate your full. This is really how you calculate your full credibility standard. I keep wanting to say, are there any questions? It's driving me crazy sitting here by myself talking. Glad we're only doing this once. Okay. Okay, so that's all well and good. So we've talked about here. I know how many claims I need for full credibility. So, or how many? So we're going to talk about this. We'll use this first number here. So I know that I need 1,082 claims for full credibility. That's fantastic. So what happens when I have 500 claims? What happens when I have, if I know I have 2,000 claims? Well, I know I'm fully credible. What if I have 100 claims? What if I have 200 claims? What if I have 500 claims? What if I have 1,081 claims? What does that actually mean? So there is a formula for partial credibility, and we could go. You can derive this. There's a lot of actuarial literature if you want to look at classical credibility. I think it's in the book how it's derived. We're not going to derive it here, but partial credibility is the number of claims divided by your full credibility standard. You take the square root. It's also called the square root of claims technique. So remember before how I said credibility is always this does fulfill the three criteria for credibility. I'm going to go back to that slide because we do actually have it graphed. Okay, so this is the shape of that graph. Again, it's strictly non-increasing and actually goes right up to 1,082. So you don't need a whole lot of claims to get to 0.2. You need more to get to 0.4. You need even more to get to 0.6, and so on. And finally, you need 1082 to get to the final. Okay, back to recording here. So the number of claims divided by the full credibility standard. The square root, or it does not be number of claims, number of anything divided by your full credibility standard. It's typically going to be number of claims or number of exposures. So number of claims divided by 0.05 is simply number of exposures. So it just changes your standard, and this the square root part doesn't do doesn't make any difference. So we have some more examples in Excel. So let's go to it. So for a second, I had the answers highlighted. I thought that I had eliminated all that. Okay, so this is our same slide here, except now we know the actual numbers of claims and actual number of exposures that we have. So let's look at our different credibility standards here. So we have 1,082 claims for full credibility, and we only have 6,000 actual claims. So what does that mean again? Remember, we said number of claims divided by the full credibility standard to the 1/2 power, or the square root. I'm going to use the square root formula. The square root of claims, number of stuff, divided by number of stuff for full credibility. So make sure you don't mix claims and exposures. That's the real thing that you want to make sure that you avoid. So 600 square root of 600 over 1082, and you get credibility standard of 74.5%. So that means if I say I need 1,082 claims for full credibility, and I have 600 claims, I believe on my data is I can use it about three quarters of it, 74.5%. So what does it mean? 600. Now, what if my full credibility standard is 271? Let's go down. Let's copy this formula. Okay, so I can believe my data now by 150%, basically. So I know I can give 110%. Can my credibility be 150%? The short answer of that, of course, is no. So I do need to have one more. I can use Excel, but basically it's a max, the min of either 1 or the full credibility standard, meaning if the standard's more than 1, I have to cap it at 1. So credibility is always capped at 1. So if this is 600 claims or 6,000 claims or 600,000 claims, still capped at 1. So regardless, anything go over 271. All right, let's slide over now to exposures. Let's look at our third one here. So we need 76,000 exposures for full credibility. So I only have 15,000. How much can I believe the 15,000 exposures? 15,000 divided by 76,000 and change, and 44%. So again, that's the one thing for full credibility. It doesn't take a whole lot of data, and this really is true when you're measuring data. It doesn't take a whole lot of data to be somewhat credible. So I have 15,000 exposures. If I want to be, plus or minus 5%, I don't need, even though my full standard is 76,000, you don't need a ton to be completely credible. So I'm just going to cheat and copy down, and here we go again. 1.397, no such thing. So I can just really use a minimum formula no matter what here. So 1%. So what if I about half the exposure needed for full credibility? So half the stuff. So 25,000 over 53,000. And that could simply also be, you could use this exact same standard. So getting about half the exposures gets you about 2/3 of the way. And that's a pretty fair thing for credibility. So half the exposures gets you about 2/3 of the way. for full credibility. Maybe closer to 70%, but I always like using the half and 2/3. Okay, let's look at something really small here. I have 663 exposures, and I only need 20 for full credibility. So I'm going to do, I could just copy down, but I really want to make this, I really want to show you the formulas again. Again, the repetition helps. So 20 divided by 663, take the square root, 17%. So 20 exposures, even though it's what, not even 5%, 5% of the exposures get you 17% of the way. So that's, obviously that is, we would expect that for the full credibility standard too. You don't have to go very far. The further you go away from one, you should always go even further from zero credibility. Okay, 100 over 102,000. Whoops, square root, sorry. Yeah, so 3%. So about 1% of the exposures gets me 3% of the way there. So that's consistent. There's always another way to know. If the more you know these rules of thumb, the better you will be for checking your answers and checking your results. So always think about those rules of thumb. So if you have half the exposure, say for example 25,000 or 53,000, and you only got a credibility of a third for some reason, you probably screwed something up. So it's always good to know those rules of thumb. I'm going to go quickly in the last one. What if this is a funny example, 383 claims, 384 exposures, 0.998. So, that shouldn't be a big surprise, but you're almost fully credible. You're essentially fully credible. 0.998. You only give 0.2% to the complement. Okay, so one thing we always like to do for this class, as you know, whenever we have a formula, whenever we have something, it always has advantages and disadvantages. So credibility is no different. So what's the advantage of classical credibility? It is the most commonly used, and it is generally accepted. So no insurance department, most actuarial departments, most of these are not going to give you a really hard time with classical credibility. So this is something that's very consistent throughout the actuarial profession because it's accepted. The data is readily available. What do you need? You need number of claims, or you need number of exposures, and you need your probability and your K. So the data is always available. The data is, I shouldn't say always, but the data is available. You don't have to do a lot of screwing around or a lot of calculations. And the computations are also very straightforward. Again, I've talked about this before, the black stuff being really black box, it might be good to actuaries, but it is not relatable to other people that you have to explain this to. So it's easy. It's an easy computation to explain, easy for DOIs, easy for people to relate to. And I can't stress that importance. It doesn't mean we're dumbing things down for people, but it's very important that you are relatable. So there's also some disadvantages, and I've talked about some of these before. So there are some assumptions that you have to do to simplify, and if you don't believe your assumptions, then maybe this isn't the right credibility standard for you, or for whatever you're working on. But it's important to know that there are the disadvantages. Again, there's no variation in size of losses. I've said that before. That's a little bit too simplifying, and the probabilities I said before are somewhat arbitrary. We pick 90 and 5 and 10 and 99 because they're kind of nice, round, easy numbers. What if it's 97.5 or 98 or 85? You could do whatever you want with the P's and the K's. But so there is some level of arbitrariness. Other thing about it is it does not consider the quality of the complement. We will get to that in a little bit, but we're not talking about the complement of credibility here at all. So your credibility should be different depending on how much you believe your complement, and we'll get to the complement of credibility later. This is I think it does the thing that does consider to be fair to this classical credibility method. The thing that does consider the quality of the complement is sometimes choosing that 384 versus 1082 versus 663 for number of expected claims. If you believe your complement really well, maybe you use a higher credibility standard for your own data. Or if you don't have a great complement, maybe you're just going to use your data more and have a higher credibility standard. So in some ways, it does consider the quality of the complement, but in some ways, it does not. Okay, gotta stop myself again. Are there any questions? No, there's not, because I'm not really directly talking to anybody. All right, so we have one more topic for credibility and for the kind of the full credibility standard, and we are going to call this Bielmann credibility. It is named after that individual up at the top, Mr. Hans Bielmann, who was one of the more respected actuaries, one of the great research actuaries of our time. This was made sometime, I think, in the mid 1900s, mid 1900s. It's also called least squares credibility. Same thing as we said before. Z equals observed experience plus 1 minus Z times this is called the prior means. This could be the actuary's a priori assumption for the risk estimate. It could be the complement too. Bielmann also always called the prior mean. You might see this in literature, and I like to give you kind of the full historical perspective of the literature. The main difference here is how you calculate Z. So it uses what's called the least squared method. We're not going to get too much into the science of it, but it is the number of n is the number of observations again. And now, what is K? So K is the variation. You're kind of looking at your experience. So how much variation is there in an individual's loss experience? That is what's called the expected value of the process variance. Then VHM is the variance of hypothetical means, or how much variance is there between all risks, and it's kind of the expected. You can see on the right there, K equals the expected of the variance of X given your risks, and it's the variance of the variance of the means, the variance of the means for every risk. So the good part about this is it does take into account your data a little bit. So if your data is so pause there for a second. Yeah. So if your data is, how homogeneous are your risks in general, or how much variance is there, and then how much variance is there within the actual risk itself. So I'm not going to go into the science of it too much. That's what it means. We talk about classical credibility a lot more, but I think it's good to know this is out there, because I think this is used in some cases. And again, maybe highlighted the cases where it's really useful. Though this is a little bit harder to calculate. So we're not going to go through the actual example. We're not going to go through how to calculate K. You're not going to expect to know how to calculate K, but the Bielmann credibility, if you went back in the PowerPoint, is kind of example 3 is a lot of the Bielmann credibility. Okay, so this really is Bielmann credibility. So it never equals 1. So depending on your K, the K will determine your shape of the curve. So if K is extremely low, you're going to see the partial credibility spike up a lot. If K is really high, you would see a shape maybe closer to this, and it would take a lot longer to get to 1. So this is example 3 is essentially Bielmann credibility, and that's where we get. Let's see, how do I get to the slide? Here we go. Okay, so the major difference between classical and Bielmann, we'll go through this in Excel in a second, but Bielmann approaches 1 as n gets large, but never equals 1. So classical credibility, you're really saying, what's my full standard, and how close am I to the full standard? Bielmann, you never actually get to the standard. So Bielmann's saying you can always add one more claim or one more observation and become more credible. And what difference does it make if you're 0.998 or 0.999? It doesn't make a difference. Okay. Remember, z equals n over credibility is z equals n over n plus k. So we have our, let me get rid of this here. So we have our variance of hypothetical means, our expected value of process, our EVPV, k equals EVPV over VHM. For interanalysis of variance, I kind of like it. It's kind of fun to look at and calculate. We're not going to do it for this class, though. I think we have quite a bit to learn here. So K is your EVPV over VHM. So 20 divided by 0 is basically what? You have no variance within your means, but your variance, your between risks is 20. So K is basically infinity, right? So 30 over 30 plus infinity equals 0 as it approaches infinity. So if your variance if your EVPV is 20, your VHM is 0, K is always going to be infinity. Now let's take the other extreme circumstance where you have no variance. You have no variance in individual's experience. So, but you have a ton of variance between risks. So again, you have no variance in an individual's experience. So all you need is one individual, and you got it, because there is no variation. So EPK in this case is 0 over 20 or 0. So n over n plus k, 30 divided by 30 plus k is 0. And your credibility is, whoops, yeah, that's right. Thank you, Excel. Your credibility is 1. So these are, obviously, I like looking at this. One of my favorite ways to learn things is to kind of look at sometimes the unrealistic or ridiculous assumptions here. So if I have a ton of variance between individuals' experience, no variance between all risks, you can't have, your credibility is always going to be 0 because there's no variance at all. There's no between variance. If you have no within variance, or your variance in individual's experience is nothing, they're all your risks are identical, completely the same, then you have full credibility because you only need one risk to be fully credible when you think about it. So 30, you can have 1 here, or you could have 99999. So those are your kind of limiting examples. All right, now let's look at something that's a little bit more normal, if you will. So your between risk variance or individuals, your EVPV is 12. I'm sorry, you have more variation of individuals' experience than you do between all risks. So K is EVPV or VHM is 1. What did I do here? Oh, I'm sorry. B7 divided by, my bad there. There it goes, 12. You have 150 observations, so your credibility is equal to, I'm just going to cheat and copy it, n over n plus k. So in this case, if you have 150 risks, you're going to be quite credible, actually, 92.6. So the nice thing, the one good thing about this is it takes away the kind of arbitrariness of limited fluctuation credibility, but it is a lot harder to calculate because you really have to know your EVPV and VHM, and that's not always in a group of thousands of data records. It's very hard to calculate. And the reason too, this is a lot of credibility for 150 observations. This is actually, these variance numbers are pretty low. Variance is usually a much higher number. So K here, K equals EVPV over VHM, 1.5 over 1.5. Your K is 1. Now your K is 1. You have 10 observations, so n over n plus k. You have, again, very high credibility. let's look at something where the VHM is 0.5 and your EPV is 56. Now you're getting into a little bit higher Ks and having 150 observations takes you 57% of the way there. So that's pretty much all we're going to talk about for what's called Bielmann credibility. So this won't be on the exam. I do like to show you this information. So I think it's good. No, I didn't go to that last slide. So Bielmann approach is 1, is get started number equals 1. Classical equals 1, where you get the full credibility. You get to the full credibility standard. So kind of same thing, only different. All right, so that concludes. Right? Oh, that's right. That's Hans Bielmann, and I love that picture because that's just some unidentified photo bomber from many decades ago. So we have no idea who that person is. I love the picture though. It's on the if you Google Hans Bielmann, that picture comes up a lot. So anyhow, with that somewhat humorous note, hope you find that humorous. That concludes that concludes section 1. So we are going to stop here and start on video 2.